thinking for some time that that I primarily came up with. There are really two basic reasons in my mind. One, because why should you study linear algebra? Well, a classical answer is because it is beautiful. And of course, beauty is in the eye of beholder. What I find beautiful, you may not find beautiful, and so on and so forth. But then I hope to convince you, and better still, I hope that by sort of reflecting on the subject and thinking about it and learning it in the true spirit, you will come to appreciate the beauty. I mean, that's really the best way to learn something. When you realize that it's beautiful, then you hardly need any motivation. But if you need some other motivation, then I can also tell you that because it is useful. Okay. Really speaking, there are two reasons to my mind that you should study linear algebra. One is it's beautiful, it's wonderful, and at least I think that way. And secondly, even if you don't, eventually find it particularly beautiful, uh, it is extremely useful both within and outside mathematics. And I'll try to illustrate this by giving you some examples. And I don't really think I can prove to you it is beautiful. This is, beauty is something which is to be uh, sort of perceived rather than explained. So, but I will hopefully try and make it clear what the subject entails and how it succeeds in solving its problems, and then maybe you will share the feeling that it's a beautiful subject, and we'll kind of come back to this answer. But that, in a nutshell, is really the answer in my mind why you should study the subject. Okay. So far so good. So now let's sort of go to the first question and try to dwell on it. Okay. So let me see. Okay. So let's start talking about linear algebra. And as you can see, uh, there are two words here. Okay. Uh, there is algebra and there is the word linear. Okay. And I want to say, and obviously, both of them tell you something about the subject. So let us remind ourselves what is algebra. And now I'm now thinking of a first year BTech student, or for who has I suppose spent about 12 or 13 years of studying in schools and colleges, and he has now come to where he or she is. Okay, so I just want to take a 1 minute quick recap of what you learn in the subject of mathematics in school. I mean, when you go to school in grade 1, you learn about numbers 1, 2, 3, 4, etc. You learn how to add, subtract, multiply, divide, take GCD, LCM. Then I don't know when, it's been a long time since I went to school, somewhere around 6th standard or something, a new fellow enters into your curriculum. And that is an extremely interesting, powerful, wonderful fellow, uh, which helps you solve all kinds of word problems. Like, I had so many apples, I gave half of them to my friend, three of them to my brother, and I'm left with two. How many apples did I have, etc. So, what is the basic technique to solve that? It is the use of a variable. You don't know something, you call it x. Okay, and whatever that apple story, that will translate into an equation. Okay, so algebra. Uh, so key object uh, in algebra is the notion of a variable, and then what that apple story would translate into some equation, maybe like ax. Let me just write x minus b equal to 0. Okay, where so this algebra, you can say, begins with the introduction of variable, typically denoted by x. Okay, uh, and equations such as ax minus b equal to 0. So, a, b, constants, uh, Allow me, I suppose it's okay. All of you have taken a course in calculus. Let me say A and B are real numbers and A is not equal to 0. Otherwise, it would be a stupid equation, which can be solved. So here, all you do is you bring the variable on one side, push the constant to another side. A is not equal to 0, x equal to B over A. This is a solution. In fact, this is a unique solution. Okay. And then your algebra course proceeds in a manner which is entirely analogous to primary school arithmetic. You learn how to add and subtract these polynomials. Complicated problems may give you to higher degree equations and so on. So you learn, of course, solving linear equations is easy. Then you learn how to solve quadratic equations. You can add polynomials, subtract one from another, divide one polynomial by another, at least to the extent you can, just like integers. And then you have you can talk about GCD, LCM, factorization, etc. All that feeds into algebra. So solving equations is one of the basic things that you do in school algebra. And of course, if you have more than one unknowns, then you may have variables like x, y, etc. And you would be led to one or more equations. For example, I don't know, 4x minus 2y equal to 10, and maybe 3x plus y equal to 6. Okay. And I think this is probably done in 9th or 10th standard. You learn how to solve this by eliminating, okay, can be solved by eliminating a variable and then doing the back substitution. Okay. And to a large extent, linear algebra has to do with such things. Okay, except we'll come back to this. All right. So, so now, so when you're studying linear algebra, oops. So in linear algebra, a basic object of study is linear equations, or actually, in fact, systems of linear equations. Okay. So I can hear somebody's caller tune. Hello. Okay.
All the
Thank you.
participants, please mute yourself.
Okay. So, in general, you may have not just one or two variables, the kind of problems you dealt with in school, but maybe hundreds of variables. So, our alphabet has only 26 letters. So, if you start calling them X, Y, Z, etc., you will run out of letters. So, mathematicians have a nice way of devising that. They just index them by positive integers, x1, x2, xn. So, let us say you have n variables, and a typical kind of equation that you just saw could be written as maybe a1 x1 plus a2 x2 etc. plus an xn equal to some other constant. So this is an example of a linear equation. And now I want to write another example, another such equation. So maybe I will call it, I don't know, a dash 1 x1 plus a dash 2 x2 plus a dash n xn equal to b2 maybe, and then maybe a double dash, but then I will get very tired of writing those dashes. So one thing what I can do is maybe so okay, so such a thing. So this is a linear equation. So for one thing that you realize, for writing several linear equations, in say n variables x1, x2, xn, it's better to use not just one subscript but double subscripts. So maybe the first equation, instead of calling it A11, let me just call it sorry, instead of calling it A1, then A11 x1 plus A12 x2, etc. plus A1n xn equal to B1. Then the second equation, now I can very effectively write it as A21 x1 plus A22 x2 plus A2n xn equal to maybe the second constant B2, and so on. So n could be 100, and I may want to write 37 equations, or in general maybe I want to write m equations. So the mth equation will look like a m1 x1 plus a m2 x2 plus a mn xn. Thank you for turning that off. And what would be on the right hand side? Well, in the first equation I had b1, second equation I had b2. This is the mth equation, so I would have a bm here. Okay. I have a bm. Okay, so this is what is called a system of equations. Okay. By the way, please stop and ask questions, or I'm just sort of really starting from scratch. So that's so okay. So maybe one definition of linear algebra could be that maybe I even wrote it down somewhere. Okay, linear algebra. So the answer to one question, first answer maybe linear algebra is the study of systems of linear equations, okay, in arbitrary number of variables and with arbitrary number of equations, and of course when you have the equations and their solutions. Okay, and already you will see that in your linear algebra course you will learn some absolutely remarkable things which you uh, may not expect. For example, just think of I have maybe 257 equations in I don't know, 300 variables. Question could be, how many solutions do they have? Is it possible that there are exactly 10 solutions or 2 solutions or 17 solutions? A priori any number could be possible, but one of the results, for example, you will prove. So let's see, a remarkable fact that you shall see in the course is that this system, I have called it star. Star can have either no solution, that can happen. For example, one equation is x plus y equal to 1, another equation is 2x plus 2y equal to 7, which would mean x plus y equal to 7 by 2. So the two equations, for them to hold simultaneously, you would have to have one equal to 7 by 2, which is impossible, so there is no solution. Or a unique solution. This is typically what happens in the kind of problems you would have seen in your high school, where you had two equations in two unknowns and you typically got a unique value of x and a unique value of y. Now, after that, there are lots of possibilities. There could be two solutions, three solutions, four, and so on. So one thing you will learn in the course is or a unique solution. If that's not happened, if there is a number of solutions is not 0 or 1, then the only possibility it turns out is that infinitely many solutions. Okay, so that's not completely obvious a priori, but that is a basic result in linear algebra that you will learn, that it can have either no solution or a unique solution or infinitely many solutions. And then you will be typically interested in trying to qualitatively understand this infinity. So to understand this infinity, you may consider a suitable notion. Let me call it quote unquote dimension of the space of solutions. Okay. Now, so how is this shown? So this is shown, and I'll come back to this, by a remarkable method. I call it a gem of a method. Okay, and this gem will stand for something so-called Gaussian elimination method that I will tell you more about. But before I do that, let me now talk about another basic object that you will study in the course on linear algebra, and that's the notion of matrices. So what are matrices? At least to begin with, that is just a nice mnemonic, nice device to write the important objects in this system of equation compactly, and in turn this system of equation in a nice way. So remember what is here. The let's see if I. Oh, so never mind. I didn't want that. Oops. Excuse me. Let me just stick to one thing. Okay. So, as I was saying, there are these a11, a12, etc. These are constants given to you, just like you had in this simple equation like this. 4x, so 4, 2, minus 2, 3, 1, etc. These are constant, which are like the coefficients of x and y, the variables. And then you have this another set of constants on the right hand side. Okay, and a nice way to represent them is by means of what is called a matrix. So you write down this a11, a12, a1n, in the first row, a21, a22, a2n in the second row, am1, am2, amn. So you write an array like that. Let me call it capital A. This is what is called a matrix. So this is a called M cross N matrix, because it has M rows, M horizontal, so to speak, lines, and N columns, N vertical columns. So this is a row, for example. This is the first row, or this is a column. This is the second column. I'm sorry. All right. And now, so your right hand side could also be written as a vector. Maybe B is B1, B2, Bm. And your variables could also be written in the form of a vector. Let me call it x as x1, x2, xn. And then that the a compact way to write star that system of linear equation is Ax is equal to B. So this matrix A, the matrix of coefficient, multiplied by this vector of variables. So what is the size of this vector? This is a, you see there are n rows and there is only one column. So this is a n cross 1. And this one is a m cross 1. This product is equal to this. What does this mean? This means exactly what is written here. So the entries of Ax will actually this product a11 x1 plus a12 x2 plus a1n xn. Okay, and that's the first entry, and then a21 x1 plus a22 x2 and plus a2n xn. And okay, so in general, we can let me we can add and multiply two matrices provided there this is right. So what do I mean by that? So here I've kind of multiplied this A with X. So A was the M cross N, X was N cross 1, and I resulted in a M cross 1 matrix or a M cross 1 column vector. And in general, AB is defined if A is say M cross N matrix and B is N cross something else, maybe P matrix. Okay. In other words, the number of columns in A should be equal to the number of rows. Okay, and this AB, so this is the product, and the resulting product will be and is a M cross P matrix if that happens. Okay, so I just want to I mean, this is something nice. In particular, if I have square matrices, then products of any two of them. Square means what? M equal to N. So products of square matrices depend. Also, A plus B is defined if say both A and B have the same size. So let's say both say M cross N. Okay, so both are M cross N. Now I just want to you to go back and reflect because then what we are doing is really we are doing things very similar to what you may have done in first or second standard. You are learning addition, you are learning multiplication, and then except that now you have new objects with which to add and multiply. And if you think about that, that already gives you a new I mean, how shall I say, new structure or a new type of what is technically called a ring, which is very similar uh, to the ring of integers, to the structure of integers that you have in school. Okay, I'll come back to this point, uh, but now let me sort of go back to this gem of a method. So gem, what is gem? This is the Gaussian elimination method. What it does basically, it so idea is start with a system of equations, so what we call star, transform it to an equivalent system, say tilde x is equal to b tilde, in such a way that so maybe I call it star star, this was star, so that this star star is easier to solve. And how is this transformation done? So so transformation done using what are called elementary row operations. Okay, you will learn this, and it's really a beautiful system. And probably for a BTech students, the best way to understand it is when you learn it in school, in your class, you write down a computer program which does it for you. So where you feed in a matrix of coefficient, feed in this matrix A, feed in a matrix B, and your computer program should try and give the solutions. Okay. Now there are so I should probably say what this elementary row operations are things which are basically transformations which result in the system in an equivalent system. So what do you do? For example, you're allowed to interchange any two equations, or you are allowed to multiply one equation by a non-zero constant that doesn't change, or you are allowed to add a multiple of one equation to another. These are the three basic types of operations that will result transform star to another system which is completely equivalent, in the sense that the solutions of this will be exactly same as the solutions of the new system. Okay. So this is something that you will learn. It's a very simple-minded method, but extremely powerful. Some keywords here uh, that you will learn is the notion of what is called row echelon form. I don't know, reduced row echelon form. Some people call it row canonical form, etc. Okay. This is a matrix in a particularly simple fashion. Okay. Very good. So now so far what have I done? I've sort of expanded on the second word of linear algebra, this one here, uh, and told you what linear algebra comprises of. It now let me also say something about the word linear. Okay, so word linear in linear algebra obviously suggests, as I mean, has to do, as the very name suggests, with lines. So, for example, lines like that, uh, or objects similar to lines, uh, such as, because line is a sort of a thing that you can do in the plane, but maybe you are in a three space and plane. So, line, plane, and so on. In general, such things are called hyperplanes. Okay, so linear algebra also has to do with these geometric things called lines, planes, hyperplanes, etc. And in a sense, and this is already now, if you sort of go back to this system here, where was that? Yeah. Think of, suppose you just have three variables. Okay, so a11 x1 plus a12 x2 plus a13 x3 equal to b1. That geometrically would represent a plane in three space, right? For if you just had two variables, like you had in this example, 4x minus 2y equal to 10. In the xy plane, that represents a line. This represents another line. And finding a solution amounts to finding point of intersection of these two lines. So that's the geometric view of this. Here, if you had three variables, then maybe you have a plane. You have then the second equation could be another plane. These two planes may intersect in a line, for example, like think of the corners of the room that in which you are sitting. Those are the planes, and they seem to intersect in lines. But now if I take, say, three planes, like the three corners of a room, that will typically intersect in a point. But of course, you could, if you were two of those planes were parallel, then there is no common intersection. Okay, and already when you think about this remarkable fact that I told you, seems kind of apparent that the system of equation has either no solution, or a unique solution, or infinitely many solutions. By the way, I have something blank. So, can somebody tell me how things are going? You are able to hear me smoothly and see what I'm writing?
Yes, we can hear you and we
Okay,
can
okay,
see.
okay. Thank you, thank you. Because it's very strange doing these online lectures. Although I'm slowly getting used to it, but all right. So really speaking, so linear algebra has to do with this line-like objects such as lines, planes, hyperplanes, it's typically like you have a 1,000-dimensional space in which you have these various hyperplanes and such, and you're trying to find their common intersection in some nice systematic way. And this is really what method like Gaussian elimination method and so on enables you to do. Okay. I want to now come back because I only have 1 hour to talk about a semester-long course. I want to say something about a few other objects, but before I do that, maybe I should say uh, what are some of the simplest systems. I don't know if somebody can answer that. If I start to think about these systems of linear equation, I already told you. And one extremely simple, I mean, perhaps the simplest system could be that all my coefficients are 0 and all my constants are 0. So the first equation is all aij's are 0, b1 is also 0. Then maybe this is second is also like that. Okay. So I have m equations in n unknowns, and both the left hand side and right hand side are 0. So here, every possible value of x1, x2, xn is a solution. I think there cannot be anything simpler than that. So this is typically a case when you have lots of equations, infinitely many solutions. Sorry. Okay. Other possibility could be that maybe my first equation could just involve variable x1, and then I have something like b1, and the second equation, and maybe I have m equal to n, x1 equal to b1, x2 equal to b2, and maybe xn equal to bn. Okay. So here what happens? Here I have a unique solution. Namely, this x1 equal to b1, x2 equal to b2, and xn equal to bn. Or something slightly more involved than that could be maybe if this x1 comes with a coefficient, maybe lambda 1 x1. Here I may have lambda n xn. So then I will have a unique solution provided, for example, that this lambda i's is non-zero whenever bi is non-zero. If bi is 0 and lambda is 0, I have a redundant equation like 0 equal to 0. I can forget about it. But if the constants appearing on the right hand side are non-zero and the coefficients here are non-zero, then the solutions are bi over lambda I. There's again a unique solution. Okay. In some sense, the equivalent system that you try to get here is, of course, not as simple as this one, but a little bit more complicated. So next to that could be that, maybe my m is bigger than n. So maybe I have lambda 1 x1 equal to b1, etc. Lambda n xn is equal to bn, and then I have the other equations, maybe just 0 equal to 0 of that type. Okay, so here, for example, I have more equations than I have variables, and let's just say for lambda is not 0, bi is not 0, solutions would be x1 is b1 upon lambda 1, bn upon lambda n, and the other things can be completely arbitrary, xn plus 1 to xm, let us say. So here, this is a situation when I have infinitely many solutions. There could be other possibility when one of the equation here has something on the so let me call it bn plus 1 to bm. So this is the case if bn plus 1 and bm are all 0. But if bi is not 0 for some I bigger than n, then I have a non-zero thing on the right hand side, 0 on the left hand side, and then I have no solution in that case. Okay. So what Gaussian elimination does for you is sort of it transforms it to something which will be somewhat similar, but a little bit more complicated than this. The point is, it will sort of bring you to a situation when you can solve things easily. For example, okay, let me your course will talk about it. Okay, now so so I want to now talk about another basic objects in linear algebra, and that is called linear transformations. Okay, so linear transformations uh, uh, okay, these are general types of maps, such as the ones that we saw, x going to a times x. What was this map doing? It was sort of taking a vector in, let me say, Rn, an n tuple, and it was mapping it to an m tuple, Rn to Rm. Okay, where A is an m cross n matrix. Okay, so let me call this T sub A. Okay, in general, T from Rn to Rm. So a map is called linear. If geometrically speaking, it takes lines through the origin, two lines through the origin, and if the following things happen, if T of, if you sort of add two vectors, x plus y is Tx plus Ty. X and y are now tuples, x and y are in Rn, which I think of it as a column vector. And if I take T and I take a multiple of a vector, then Tx is equal to lambda x, again for x in Rn, and lambda some scalar r. R is the set of real numbers. Okay, so such a map satisfying these two properties is called linear, and a basic example is given by this map, and it can actually, you will show that essentially this is the only example of a linear map from Rn to Rm. Because conversely, if you are given a map from Rn to Rm, you can associate to it a matrix A such that it will look like multiplication by A. Okay, and so then in general, linear transformations can be defined more generally on subspaces of Rn. So this is one word you will learn. So what is a subspace? Subspace is a space. For example, Rn itself is a subspace. But if I have a that is so V, a subset of Rn, such that whenever I have two vectors in V, x plus y is in V, and whenever I have a vector x in V and a scalar lambda, lambda times x is in V. Okay, and maybe I will assume for simplicity that this contains at least one vector, namely the zero vector is in V. Okay. Anything with these properties is called a subspace. Okay, and you can there are many examples of subspaces. So and essentially the linear transformations you see will be defined on subspaces of R. How much time do I have? Hello?
As we started late, you can take 10-15 minutes more if you want to.
Okay. So now I want to I want to say something about what are called eigenvalues and eigenvectors. Okay, so these are things associated to okay, maybe even before I come to that, to square matrix. Square matrix means A, say n cross n, or to a linear transformation T from a vector space to itself. See here the linear transformation was from Rn. This vector space, domain vector space, was different from the range, the codomain. But if I have a map from V to V, then there are some special numbers which are called eigenvalues and eigenvectors. In fact, before I do that, let me. So what? Oh, so what are eigenvalues? So let me make a definition. Okay. So let's say lambda is an eigenvalue of A if Ax equal to lambda x for some vector x different from 0. For some x in Rn, x different from 0. And such a vector x is called an eigenvector of A corresponding to the eigenvalue lambda. Okay, eigenvalue and eigenvector, and some other names are for characteristic value, characteristic roots, etc. And these are really, I mean, it turns out that if you are given an n cross n matrix, then there are only finitely many numbers, which at most n, which can be eigenvalues, and then they can have eigenvectors. And in if okay, so what about this was for a matrix? In the case of linear transformation, T from V to V, that would be lambda such that uh, T of let's say T of V is equal to lambda V for some vector V in V, V not equal to 0. Of course, if I take 0, then A times 0 will be 0, then any lambda will be eigenvalue. That would be stupid. So this condition is very important. And then you have a similar notion of any such V is called an eigenvector of T. Okay. Okay. Now, the fact any n cross n, say let's say matrix, real matrix, has at most n eigenvalues, which may be real or complex. And the way you find them is by solving what is called a characteristic equation. So this kind of brings us back to high school algebra, polynomial equations, and so on. And what that involves, what that involves, let me sort of go to a new page, is a notion of what is called a determinant. Okay, this determinant is a completely magical object. So this determinant is if I have a n cross n matrix, then to that I can associate a single number, which is denoted by determinant of A. So let's say with entries in R, then this is a real number, and this captures a lot of information about the matrix A or the corresponding system of linear equation. For example, if I have a system like Ax equal to B, where A is a square matrix, it turns out that this has a unique solution if and only if the determinant of A is not equal to 0. Okay, and so eigenvalues so in particular, in some sense, this will mean that Ax equal to 0 has where I take the 0 vector has only the trivial solution, namely x equal to 0, if and only if determinant of A is not equal to 0. Okay, then the only solution is x is the 0 vector. So eigenvalues can be found by considering, see, remember I had the equation Ax equal to lambda x, which if I push to the other side, I can take lambda x, so lambda minus A, or lambda times what is called the identity, is equal to 0. So that means I want this equation to have a non-trivial solution. And if determinant of lambda minus A would be non-zero, then this will not have a non-trivial solution. So by considering the equation determinant of the I minus A, I is equal to 0 as a polynomial in lambda and finding its roots. And okay, so oops. And just I want to say one last thing, and that is the notion of what is called diagonalization that you will learn, which is that when is a and that when is a square matrix A similar to the kind of square matrix for which I had a very simple system of equation to a diagonal matrix. The word similar has a technical meaning which will be explained to you in your course. That is, diagonal matrix means a matrix of the form lambda 1 0 0 0, then 0 lambda 2 0, and so on, 0 0 lambda n. So it just has only possibly non-zero entries on the diagonal, but off diagonal entries are all 0. So such a thing is called a diagonal matrix. The transformation that it corresponds to is just x1, you know, so you have a vector x1 x2 xn, and that will go to lambda 1 x1, lambda 2 x2, lambda n xn. So if you were to write down the corresponding system, it will be extremely simple to solve. Okay, and very good. So I guess I don't have time here because I do want to talk a little bit about uh, the uh, about the utility of linear algebra. So, so how is linear algebra useful? A large variety of problems that actually come up can be often reduced to questions about matrices and linear equations and linear transformations and so on. So uh, and so that's one way in which sort of you can find uses of linear algebra. But one of the things that linear algebra does for you, it kind of gives you this new play objects called matrices, and you can talk about their linear algebra, and that gives rise to structures which are of interest in themselves. So so the ideas and methods of linear algebra in useful in many branches of mathematics, some of which you will learn. For example, multivariable calculus, which you may have learned to some extent, or differential equations, which you will learn immediately after linear algebra. And really just about anything that you will study. For example, let me just say abstract algebra, uh, where you study objects which are somewhat more general than these subspaces. Um, Even number theory, the list is almost endless. Combinatorics, there is something called Lie groups and Lie algebras, which really matrices will play a very, very fundamental role in that kind of a study, uh, and so on. What is called algebraic geometry. Algebraic geometry, in a sense, you can think of as a generalization of linear algebra, where you don't just study systems of linear equations, but polynomial equations. Then what is called differential geometry, and so on. Okay, but so it is therefore imperative that you have a good grasp of linear algebra if you want to sort of you know continue to study and enjoy mathematics. But I want to talk about some practical applications and mention one in particular that almost revolutionized the way we conduct ourselves today. Okay, one of the striking applications of linear algebra in somewhat more recent times is that it's a fundamental tool in the Google PageRank algorithm. I'm sure all of you have used Google to search something or another, and invariably you will find that whatever you are searching for, the first few pages that are shown up have uh, have the most relevant information for the keywords that you search, and this is not an accident, and this happens by an elaborate algorithm which has at the back of it really methods from linear algebra. Um, Indeed, the things that I talked to you about, eigenvalues, eigenvectors, and there is something a little bit more advanced called Perron-Frobenius theorem, etc. So I mean, I think your generation is such that you took internet and Google for granted. Uh, the internet developed more or less in front of our eyes. When I remember in early 1990, when I joined IIT, there was only one computer in whole of IIT Bombay which had internet access, and the World Wide Web search engines in those days were extremely primitive. That so you want to search for some phrase called Jodhpur, it will probably just look and list all the pages which has that word Jodhpur in it. And but then how do you know what is the most relevant? So you need to rank the pages in order of importance, and that was something which was thought about by two young graduate students who wrote a paper. Uh, yeah, so I think the names are uh, Larry Page or Lawrence Page and Sergey Brin. Okay, well, you can Google it. And in fact, they said in that the first line in that paper, it's very interesting to read that we propose a search engine called Google. The Google comes from a variant of the word Google, which is a very large number, I think 10 to the power 100 or something like that. So and they propose this PageRank algorithm, which in an extremely essential way uses linear algebra. Uh, so, by the way, these two were at the time graduate students, like what in India we would call postgraduate students in Stanford University. So the early algorithm were actually patented, but the Stanford University held that patent. It was later that these people founded Google company and became multi-billionaires. And so if you sort of want to learn something about that, probably since I don't have time, you can try to Google PageRank algorithm. In particular, I recommend to you, there is an article called the 25 billion dollar eigenvector. Okay, so so it is just possible that you know your linear algebra well, and you could possibly even earn billions of dollars. But because it's really a very clever application of linear algebra, which is what this Google PageRank algorithm is. But let me sort of mention some other uses. Uh, Optimization, uh, including the keywords you may have heard about, linear programming, etc., which uses techniques of linear algebra. Optimization actually has to do with not just solving systems of linear equations in several unknowns, but possibly also inequalities, where you replace the equal to sign by something like less equal, etc., and you try to find a solution which is in some sense optimal. And again, the techniques of linear algebra will be extremely important. Uh, Today, even the so-called data science, artificial intelligence and machine learning, will use linear algebra and methods of linear algebra in a very essential way. Um, Other applications I want to mention. Okay, let me just throw in a keyword because I'm running out of time. There's an important field called cryptography, and there is something called coding theory, which has a direct impact on the life that we live today. So, for example, what is okay? Let me explain a little bit. Coding theory has to do with sending secure, you know, to be able to uh, do efficient transmission of digital messages. So these digital messages, this could be music, this could be a video file, this could be a conversation that happens over mobile phone. This will amount mathematically to a large string of zeros and ones, and you send it across in an effective way, so that if even if some of your zeros becomes one or ones become zeros, you are able to retrieve the original message, okay, in some efficient manner. And that is done by means of so key object in the subject of coding theory is what are called linear codes. And linear codes are really nothing but subspaces of space like Rn, except that the field of real numbers is replaced by some what is called a finite field, just consisting, for example, of 0 and 1. Okay, and again, linear algebra is extremely basic to the study of coding theory, which in effect is essential for um, sort of error-free digital transmission, uh, including, for example, linear codes were used in sending data from the Mariner satellite which went to Mars. Mars is again in vogue now, and quite possibly they are using linear codes there. Cryptography has to do with the sort of things you would be doing online, such as paying your fees, making a credit card transactions, and so on. And the way you ensure that it is done in a safe way is done by means of crypto. I guess uh, is my time over?
No, you can take a couple of minutes if you want to.
Okay, okay. So for example, one of the things that is done in cryptography, I just mentioned the keywords here, is called stream ciphers, or there is something called LFSRs. That means this stands for linear feedback shift registers. Okay, this is a very classical device used in cryptography, and again at the basis of it are matrices, linear recurrences, and so on and so forth. Okay, so LFSRs and their advanced variants called word-oriented LFSRs play indeed an important role in cryptography. Um, so, in fact, it's really amazing in how many ways linear algebra is applied in our day-to-day life. We may not we may not think about it when we use a mobile phone, when we use a credit card, uh, when we read a page from the internet, when we Google something. Really, somewhere at the back, you are doing linear algebra, and of course, the future is open, so there could be many more uses. And I hope that some of you who are listening to this talk might be instrumental in bringing about these uses, just like these two students, Larry Page and Sergey Brin, revolutionize web search with their Google search engine. Uh, what are some of the sources? I guess today, again, you can your teachers will tell you, but there are excellent books and papers and articles and even videos that you can find on the internet or in your library, which tell you a whole lot about linear algebra. I have only, I should say that I've sort of scratched the surface, but tried to tell you of some essential ingredients of the subject and indicated to you where all it can be applied. I don't mean to give you an exhaustive list. Quite possible that your teachers will tell you more about applications of linear algebra. Just so at the end of the day, then I just repeat the answer that I gave uh, to the question, why study linear algebra? And I really have just these two things to say. It is, I repeat, beautiful. It's really a beautiful subject which largely succeeds, and it is useful. Okay. And I hope that over the course of the semester and possibly even afterwards, you come to realize both the beauty of the subject and possibly the utility of it, and you enjoy the journey. I think let me stop here. I have exceeded my time. I thank you for your attention, and I'm happy to take any questions that you may have. Okay, thank you.
Okay. Thank you, Professor. Thank you for this nice talk. I hope the student got motivation from your talk to study linear algebra and pay attention in their course, except getting just good grades. Okay, so any questions for Professor? Students? You can type in chat, or now let me give you, okay, you can unmute yourself and ask. Please unmute only if you want to interact with Professor. Any questions from students? Sir, from the previous chat, I can read one question that some
Yeah.
student is asking that in daily life, when do we use linear equations?
Sorry.
In daily life, when do we use linear equations?
In daily life, when you use linear equation, I sort of indicated to you. In fact, when you're doing your Google search, you are in effect using linear algebra. So that, and since I told you that linear algebra has largely to do with solving systems of linear equations, you are doing that. Uh, but many word problems of the kind that you saw in school, but much more general variants of that can be formulated in terms of linear equations, and then the answers to that will depend on finding solutions of linear equations.
Thank you, sir. So one student is asking that how can we visualize linear algebra like calculus is easy to visualize?
How can you visualize linear algebra? So that brings me to the geometric interpretation of what I told you about the linear equation. See, just like if I have a linear equation ax plus by plus cz equal to d, that will represent a plane in 3 space. If I have two linear equations and I'm trying to find their simultaneous solution, it's like intersection of two planes. Okay. If I have three planes, so you can very well visualize intersections of planes in 3 space. But if you have a more fertile imagination, you can visualize planes like objects in I would find it a little bit difficult to imagine or make pictures at any rate beyond dimension 3. But I understand that physicists probably make some pictures. For me, the best way to think about n dimension is to just write x1, x2, xn. But if you can stretch your mind and you visualize an n-dimensional space, and you have planes or plane-like objects, say hyperplanes, and you really speaking, you have lots of hyperplanes, and you're trying to study their intersections and so on, or transformation of one to another, etc. So that's one way of what linear algebra is about.
Thank you very much, sir. If there are no more questions, I thank Professor Sudhir Ghorpade for this wonderful talk. Thank you, sir.
Thank you, and again, apologies for the delay in starting and the technical
I
issues.
also apologize for technical issues in the beginning and delay of the talk in the beginning. I'm very sorry for that.
No, it's actually more my fault, but okay.
No, it's fine. Okay, so bye everyone. I hope you got motivations to learn linear algebra. Just getting good grades are not enough. There should be some other motivation. Thank you very much, sir.
Okay,
Thank you for this wonderful talk.
Thank you. All
Bye.
the best. Yeah.
Okay, thank you. Bye.
Okay.